Okay. And uh, I think up to now, maybe you have that idea already. Okay. Up to now, we have completed some major parts. Okay. Some major parts. Okay. The first one is sampling. Okay. First one is sampling. Okay. Um, so under the sampling, we have discussed some uh, properties of discrete sinusoidal signal, okay, sinusoidal signal, okay. One of main properties we have discussed that, okay. Once we discrete a sinusoidal signal, okay, so if we have a continuous time sinusoidal signal like this, xt a cos 2 5 ft plus 5, this kind of sinusoidal signal, okay. So this is a discrete time, okay. It is a function of time, okay. If we have uh, sampled this, some sampling time Ts, okay, and maybe you can remember that sample frequency is equal to 1 over Ts, okay. Now, once you sample this, we will have a discrete time signal xn, okay. So it is a cos 2 5 f. Now, instead of this t, you can apply. So maybe you can remember that the samples. So here we have in the discrete time signal, we have represent the sample number n. Okay. So in the continuous time, the signal is representing time directly, time with respect to voltage or something. But in a discrete time signal, we use n rather than t. Okay. So this is sample number. This is sample number. Okay. Some sample number. It can be minus infinity, plus infinity, integer 0, 1, 2, minus 1, minus 2, minus 1, 0, 1, 2, 3, so on up to minus infinity or plus infinity. It is an integer. Okay. But this integer n is related with the time. Okay. So the corresponding time is equal to n ts. Ts is the sampling time. This one, sampling time. This one, ts. Okay. So you can. So now once you discrete, we have some sample. Okay. So related sample time. This t you can represent using nts. Okay. NTS like this. So the phi is there, the phase is there. Now, you know that this relation, okay, the sampling frequency is equal to 1 over sampling time, okay. So you can substitute this 2 5 f, substitute this fs instead of ts, so it will be n over fs, okay, n over fs like this, okay, and the phi is there, okay. So this is the discrete time signal, sample signal, okay. So maybe you can remember that this part, this is the frequency of the discrete time signal, f divided by fs, okay. The continuous time frequency divided by the sampling frequency. This is the frequency of the discrete time signal, and we called it the normalized frequency. Normalized frequency. Okay. We use capital F or simple F to denote this. Okay. So anyway, this is a normalized frequency. This is a normalized frequency. Okay. And maybe you can remember that. Okay. That is one major properties we have discussed. Okay. This F, this normalized frequency of a discrete time signal is between minus half and plus half. Okay. So this relationship is very important. Okay. So you better remember this one. You better understand this one, this concept. Okay. So for a discrete time signal, normalized frequency is between minus half and plus half, but in continuous time, that frequency can be from minus infinity to plus infinity. Okay. But here, all these frequencies will be within this range, okay? And you know that another relationship, okay, omega is equal to 2 5 f. This omega is normally referred as angular frequency. angular frequency. Actually, that is angular velocity, okay? But sometimes we refer it as angular frequency. That is radian per second. We measured this using radian per second, and this F is the frequency that is used in hertz. Okay. So this normalized frequency F over Fs, if you multiply it by 2.5, F over Fs, that is capital or simple omega. So this is the normalized angular frequency. Okay. So you can't get normal frequency. If you have the normal frequency, you can't just divided it by the sampling omega, and you can't say that it is omega. I think this relationship is not correct. Okay. You have to go like this. Okay. So this is the sampling omega. Okay. So if you consider this omega, okay, so it is 2.5. So you have to multiply this by 2.5. So this also by 2.5, this also by 2.5. So this will be omega, the normalized omega, okay, normalized angular frequency, and it is between -5 and +5. Okay. So omega is between -5 and +5. We have discussed these things. Okay. So that is one property. I just remind you. Okay. So sampling and properties of discrete time signal we have discussed. This is one property. Okay. Then we come to Fourier analysis. Fourier analysis. Okay. Fourier analysis. Maybe I'm not sure. Okay. I'm not 100% sure. Okay. I will check and let you know it. Okay. Uh, the sampling part will not come to your final exam, most probably, okay? This part will not come to your final exam, okay? But this concept you should remember, because sometimes this concept you have to apply, okay? You have to apply for questions, okay? So you need to remember those things also. But Fourier analysis will come to your exam, definitely, okay? So under Fourier analysis, maybe you can remember that basically we have learn two types of analysis techniques. One is Fourier series representation. Fourier series representation. We use complex exponential Fourier series representation for a discrete time. Okay. This is for periodic signal. Periodic signal. Okay. And we discuss discrete time Fourier transform. This is for non-periodic signal. This is non-periodic signal. Sometimes we refer it as Fourier transform, just Fourier transform, okay? So we have learned these two types, okay? So you need to do some example in this, okay? And try to remind this concept again, okay? Then we have discussed the sample type of Fourier transform, that is we referred as DFT, discrete Fourier transform, okay? So we have used the basic equation to calculate DFT, discrete Fourier transform. So go through this again and try to remind it. Then under DFT, we have discussed two types of algorithms, to calculate the DFT, discrete Fourier transform. That is we called decimation in time fast Fourier transform, FFT. Other one is decimation in frequency fast Fourier transform. Okay, so these two algorithms also we have discussed. Okay, so I have uploaded one example. Please try to go through it and please be familiar with these things. Okay, so once we have completed Fourier analysis, we move to Z transform. Okay, so Z transform. The Z transform stuff also will come to your final exam, definitely. Okay. So under Z transform, we have discussed the basic definition of the Z transform. Okay. Then we have discussed some properties of Z transform. Okay. Like time shifting, frequency shifting, convolution property. Okay. And differentiation in time domain property, this kind of properties we have discussed. Okay, in those lectures, some properties are there. So try to go through it and be familiar with those properties also. Okay. So once you have complete the properties, okay, we have discussed about inverse Z transform. Okay. So inverse Z transform is somewhat complex, okay, because you have to do the contour integration to evaluate the Z transform, inner Z transform directly. So it is not in our scope, okay? So that is a complex mathematical process is there, okay? So we haven't used that direct inner Z transform method, okay? But we have used some techniques to calculate Z transform. One is by examining the Z transform function. Z transform function, we can conclude the uh, inner Z transform, the time domain signal. Okay. So by looking at the Z transform, the definition. Okay. So here, so we have used the definition for that. Okay. By looking at the definition, we just conclude the uh, time domain signal again. That means we found the inner Z transform. Okay. And also we have another technique that is a partial fraction techniques. Okay. So we have discussed some example with these things, okay? So be familiar with the inner Z transform, mainly using the direct method, okay? The definition of the Z transform, and also the partial fraction method, okay? So that is that. Then finally we have discussed, I have discussed, okay? But I think up to this one we have discussed in our classroom, okay? But this one we haven't time to discuss, okay? But I have uploaded the recorded session. Please go through it. If you have any problem, please ask me. Okay. Then we have discussed the stability of a system to analyze the stability of a system using Z transform. Okay. So there we have found the we should need to verify the pole zero plot. Okay. Then based on the location of these poles and zero, we can conclude the system is stable, not stable, or marginally stable. Okay. So these mainly these four things we have discussed on the Z transform. Okay. Please go through it and be familiar. The Z transform question will come to your exam definitely. Okay. Okay. And now we have to discuss about the system design. Okay. System design. Okay. System design and analysis. System design and analysis. Okay. Analysis. Okay. Actually, these are discrete time signal. Okay. Discrete time signal systems design and analysis part. Okay. We have to discuss. Okay. So to cover this session, okay, we mainly focus on FIR filter design. Okay. FIR filter design. FIR filter design. Okay. So this is our main topics actually. Okay. FIR filter design. Okay. So we will see this one. Okay. So this part also will come to your exam. Okay. Uh, okay. So this is just uh, just guide to uh, prepare for the final examination. Okay. So please go through this and if try to do some example as much as possible. So if you couldn't do any example, please let me know. Okay. Then I will try to do it. If I couldn't try to do this, okay, we can get help from Dr. Udesh also. Okay. So so if you have any problem, you can contact me. Okay. So if I can't give you a solution, I can get the help from Dr. Udesh, then I can give you a solution. Okay. So, uh, so do as I told you, okay? Try to do the example as much as possible. If you have any problem, please let us know, okay? Okay. So we will move to the FIR filter design, okay? Uh, FIR filter design, okay? So before that, I think I have remind you this several times, as I can remember, but for the completeness also, I will explain it here also, okay? So if you consider a LTI system, linear time invariant system, okay? If you give a time domain input, and you will have a output like in, okay? And the impulse response of the system is, let's say that delta n, okay? So the output is equal to input 1 mole delta n, okay? This is the convolution. Okay. So you have to perform the linear convolution or circular convolution to evaluate the yn. Okay. If you know xn and delta n. Okay. But if you know yn and xn, you can't evaluate delta n because the reverse process of convolution is somewhat hard. Okay. Maybe impossible. I don't know. Okay. So we use another techniques to find this delta n. So that is, okay, so this delta n is the impulse response, okay, this is the impulse response. Sorry, it is normally referred as hn, okay, I'm sorry. Delta n is the impulse, okay, sorry, don't get confused, okay. Delta n is the impulse, okay, hn, okay, hn is the impulse response. So this is the hn, okay, I'm sorry. Hn is the impulse response, okay? So Hn means the impulse response. That means if you give a impulse, delta n to the system, the output is referred as Hn, impulse response, okay? So that is the impulse response, okay? Actually, still I don't know. It is decided by Dr. Udesh, okay? As I can remember, he said that this will be a closed book exam, okay? I'm not sure about it, okay? But he said that this will be a closed book exam, okay? But you no need to keep remember mainly the equations, okay? The basic equation try to remember, but the complex equation maybe not, no need to remember all these things. We can give it to the exam, okay? Uh, so the basic things maybe it is better to keep remember, okay? I don't know the Dr. Udesh decision. Okay. So sometime if I make the paper, okay, he do some changes actually. Okay. So it is better to ready for any things. Okay. So try to remember the basic equations, maybe for the Fourier transform things. For example, the basic Fourier transform definition, basic Fourier series definition, DFT definition, then Z transform definition. Those things you can keep in remember. Other things maybe not need. Okay. 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 So so to calculate this HN, we can use a technique. We can use a procedure. Okay. So that is, if we know the YN, we get the Z transform or frequency transform, Fourier transform of the yn. So that will be yz or y omega. Okay. And then you get the Fourier transform or z transform of x is xn. That is xz or x omega. So this is the complex domain signal xz. And this is the frequency domain signal x omega. Okay. So using z transform or Fourier transform, you can convert this xn or yn to the complex domain. If it is complex domain, that is a transform, or you can convert it to frequency domain using Fourier transform. Okay. So then you can get this impulse response also. You can convert into Z or into this complex domain or frequency domain using Z transform or Fourier transform respectively. Okay. So it will be H Z or H omega. Okay. In this time, we are mainly we are mainly concerning about these things, Y omega, the frequency domain signal, frequency domain representation. Okay. So if you consider this one in both cases actually, okay. So you can write this equation Y omega, X omega. Now this convolution will become simple multiplication H omega. Okay. So it will be like this. Okay. Then H omega, you can refine as Y omega divided by X omega. Okay. So, now this is just a multiplication. Okay. So if you know the Y omega, if you know X omega, you can get the division, then you can conclude the H omega. Okay. So if you want to find Hn, you have to get the inverse Fourier transform of H omega, then you can find the Hn. Okay, so that is the technique we use. Okay, this is the convolution property. Okay, this convolution become multiplication. That is the convolution property. Okay, using the convolution property, we can write this. Okay, this is convolution property. Okay, okay. So now you can calculate this H omega. Okay. Now, and also the same you can do in the Z transform also. Okay. So, if we uh, take frequency domain. Okay. So normally this is referred as transfer function, or simply response. Also, it is referred as response. Okay. Most probably it is referred as a response. Okay. That is the Fourier transform of the HN, impulse response. Okay, so it is in frequency domain. Sometimes this is called as frequency transfer function or frequency response. Okay, if it is Z domain, it is complex transfer function or sometimes referred as complex response. Okay, so this is in frequency domain. So H omega is normally referred as frequency transfer function, and H omega also referred as frequency response. Okay, okay, and one thing I need to tell you. Okay. So now this is frequency domain. Okay. So if you are given input X omega, the output is there Y omega. Okay. Now Y omega divided by X omega. Output divided by input. This term has another word. Can anyone remember? මේ term එකට කියන තව නමක් මොකක්ද? For example, maybe can you remember the amplifier if you consider just a transistor amplifier? Okay. If you just consider the transistor amplifier like this, okay. This is the common base, common emitter configuration, okay. So input is the input signal is given, okay. Let's say that it is V1. The output is there, V2. Then input V2 divided by V1. This is referred as what? Can anyone remember? What is this? The input divided by. So here it is actually in case of amplifier, we are normally getting the voltages. Okay. So output voltages divided by input voltages. Output voltage divided by input voltage. What is this? Can anyone remember? Output voltage divided by input voltage. What is that? I know the terms. What is this? Amplifier what? This is we called amplifier. What is this? This is we called amplifier. The output divided by input. What is this? Amplifier gain. We refer this as gain. Okay. So if we are consider voltage, it is voltage gain. If we are consider power, it is power gain. Okay. So here also you can see that output signal divided by input signal. This is also a gain. No? This is also a gain. Okay. So most probably this will be some voltages. Okay. The voltages with respect to omega. So these are voltage gain most probably. Okay. So if you get the magnitude and square it, okay, magnitude and square it, okay, y omega magnitude and square it, okay. So this will be power. This is the power gain of the system. Okay. So this is the power gain of the system. Okay. So please try to understand this one also. Okay. So this is input divided by output. Okay. Most probably, if this is the voltage square is the power, no? Normalized power. If you get the voltage square, you know that power is equal to voltage V square divided by R. If this R is 1 mole, that is we call normalized power, the power is equal to V square. Okay. So here also the normalized power, you can find the systems, okay, using by getting the absolute value and omega square it, okay. So that is we call power gain, okay. So this is the power gain of the system, okay. So so um, uh, so most probably sometime, okay, sometime if you want to design a filter, if you want to design a filter, okay, filter, okay, we are given this H omega. We are given this H omega, okay. So sometime this H omega is given as H omega square, okay. So that is the power gain. The power gain is given, okay. So according to the power gain, okay, you can design the filter, okay. For example, I will show you, okay. So maybe when we are designing microwave filters, okay, using lumped element, okay, that means using inductor and capacitor, okay. Uh, we that is the first thing we should refer, the response of the signal, response of the filter, okay. Mm, okay. So actually in this course, we are not going to realize the filter, okay. We are going, the design means here, the design means realize. That means we implement the filter using LCR, inductor, capacitor, and resistor, okay. But in DSP, we are not going to realize the filter. We are not going to implement it using lumped element, or sometime you can use op amps also to realize analog digital filters, okay. And these are analog filters actually. Using lumped element, we are making analog filters, but you can use op amps, that kind of things to develop digital filters, okay. But we are not going to develop them. And also, sometime maybe you have to code it, okay. So using a PIC, you can get a PIC or some embedded system, then you can code it to have a filter. Most probably there is a called filter called adaptive filter. So for the adaptive filters, actually it is very hard. I don't know whether it is possible or not. Okay. Uh, Using the element, it is somewhat hard to implement. So we have to decode, we have to code it. Okay. So anyway, okay. So if you want to realize a filter, okay, actually these are called the frequency selective filter, because these filters are uh, working on in the frequency range, specific frequency range, that is we call the pass band, okay. So these are called as frequency selective filters, okay. Actually, in this course, we are going to design FIR filter. Those are frequency selective filters, okay. Frequency selective filter. Remember that one also. This is frequency selective filter. That means uh, the filter is operating between the specific frequency range, okay. And this specific frequency range we called as pass band, okay. Pass band, okay. Okay, so for example, this is so based on the function also you can classify the filters, okay. So there are commonly used three functions, okay. This function, okay, actually the response, the function means the response, this one, okay. So this one. So you can see that this is the response, okay, H j omega, and you can see that it is squared and you get the 10 log. That means it is in dB, okay. So here, in this case, the H omega, okay. So sometimes this is referred as H j omega also, okay. So in that case, it is referred as H j omega. Then you have square this. That means you are going to get the power gain, power response, okay, power response. Then you have applied 10 log 10. That means you convert this into dB scale, okay, decibel scale. So these two come here and it will become 20 log 10, okay. Uh, Okay. So here, uh, for this design, okay, for this design procedure, uh, they have used the power gain in dB. Okay, this is the power gain actually. Okay, so this is the power gain. Based on this power gain, the the the, the shape of this power gain, you can you can classify a filter into mainly three parts: Butterworth, Chebyshev, and elliptics. Okay, so Butterworth means this kind of one. Okay, so here this is the uh, uh, pass band and this is stop band. So pass band is flat, stop band is flat. So that is we call Butterworth. Okay, Chebyshev means that is not the pass band and stop band, not smooth, flat. Okay, so here you can see the Chebyshev filter. In the Chebyshev filter, the pass band has a ripple. Okay, and for the elliptic filter, pass band and both stop band has a ripple. Okay, has a ripple. So that is elliptic. Okay, so that is based on the function. Okay, so these are not in scope. Okay, but I want to show you that when we need to realize a filter, okay, you need to use this power gain, power response. Okay, this is also referred as power response. Okay, so this is the Butterworth power response. It is like this. Okay, okay, so you have to use the power response, then you have to calculate the filter uh, order, then you have to calculate the element value. So there is a designing procedure there. Okay, so that is well documented. The standard designing procedure is there. So it is easy. If you are familiar with this process, then you can do any design. Okay. So what I want to tell you is here that, okay, this, this gain, this gain, okay, this gain is, should be given to design a filter. Okay. Or if this is not given, we have to find this. Okay. We have to find this to design a filter. Okay. But here, we are mainly concerning to design a filter if the H omega is given. Okay, H omega is given. Actually, here designing filter means we are finding the uh, time domain signal, time domain in response. Okay, so this is the frequency response, and we are going to find the time response, that is the impulse response. Okay, so we are mainly referred to this FIR filter design means that you are getting the the impulse response with from the frequency response, frequency transfer function. Okay, so that is you have to apply the inverse Fourier transform. That is we normally referred as filter design. Okay, if you, so this is also important when you are designing a filter. Okay, so if you are coding, maybe using in MATLAB also, if you want to design, if you want to implement the filter in MATLAB, so this time domain signal, time domain response will be important. Okay, I will tell how it is important. Okay, later. Okay, so that is the main things we are considering here. Okay, so okay, so as I told you, there are many filter classification. There are many filter classification. Okay, filter classification based on different parameter, based on different parameter. Okay, different parameter. Okay, for example, one classification is the uh, if the filter is responding with a specific parameter, we called it frequency selective filter. Frequency selective filter. Okay, or if it is not, it is a uh, non-frequency selective filter. Okay, So here we are mainly focusing of frequency selective filters. Okay. So in frequency selective filter, there is a specific band. Okay, a specific band that this filter is operate. Okay. So based on the band also, based on this band also, we can classify a filter into mainly four parts. Okay. That is low pass filter, high pass filter, band pass filter, and band stop filter. Okay. So this classification is uh, depend on the frequency range of the filter. Okay. So if it is a low frequency range, we call it low pass frequency. If it is a high frequency range, high pass frequency, or specific band, it is a band pass filter. Or if we need to stop one specific band, that is a band stop filter. Okay. So these four types of filters are there. So this filter classification is based on the frequency range of the filter. Okay. Okay. So if you refer, when you are referring Dr. Udesh lecture note, okay, so you can see that, okay. So we are using frequency selective filter, okay, and this is the story I have explained, okay. Uh, then this one, okay. Uh, so this is one, okay. So the ideal filter means the perfect filter. Okay, actually perfect filter we can't realize in a real world. Okay, so this is not the practical filter. This is a perfect filter. Okay, ideal filter. Okay, mathematical filter. Okay, so the ideal response is given like this. Okay, given like this. The h omega c e to the power minus j omega, so like this. Okay, so you can see that this is omega. Okay, this is omega. This omega is between some specific band and zero otherwise. Okay, I will explain this. Okay, I'm not sure about this part. Okay, zero otherwise I'm not sure, because we are normally getting this omega is between -5 and +5. Okay, so most probably this should be -5 and +5. Okay, okay, anyway. Okay, so let's say that uh, if we have this kind of h omega is given as c e to the power minus j omega minus j omega. I will use alpha here, okay? Instead of n naught, I will use alpha. C minus j omega alpha. This omega is between some frequency omega c minus omega c and between plus omega c. Okay, like this. Okay, and zero. Okay, zero. I will write like this. Okay, I will write like this. Omega c less than omega greater than omega c. Sorry, greater than 5. Greater than omega c and less than 5. Zero. Okay. I hope we have, if you put like this, that is correct. Okay. I'm not sure about this. Okay. But anyway, I want to write this should be omega is between omega c and +5, and omega is less than -5 and greater than minus omega c. Okay. So this is I want to find that. Actually, this is I want to write. Okay. So I hope you can write this as omega magnitude less than omega c plus omega, sorry, plus 5 like this, okay? I will explain this, okay? What is this, okay? If you couldn't understand this, okay? I want to write this actually, okay? So omega is between omega c and plus omega c and 5, and omega is between minus 5 and minus omega c. That is what I want to find, okay? What I want to write, okay? Let's say that I want to find, if I plot this one, if I plot this one, okay? If I plot the h omega, okay? I will plot the h omega magnitude. I will plot h omega magnitude here, not h omega. I'm going to plot the h omega magnitude, okay? Actually, as I told you that we are mostly concerning about h omega magnitude square, the power response, okay? So I will use h omega magnitude. I'm not getting the power square, but I will get h omega magnitude. Okay? So if I want to draw the h omega, okay, h omega, this one, can you draw this? Can you try to draw this? What is the magnitude of h omega? So you can see that omega should be between minus omega c and plus omega c, okay? And this is minus 5 and plus 5, okay? So this is, what is this range? This one, no? This is the range. Minus omega c and omega c. Omega is between minus omega c and omega. I'm drawing omega with respect to h omega, okay? So omega is between minus omega c and plus omega c. So this is that range, okay? So what is this range? Less than minus 5, greater than omega c. That means this range, no? This range, this range. Then omega c less than omega c, greater than omega c, and less than 5. That means this range. So actually, I want to define this range, and this range, okay? So that is, I use this one, okay? I hope this range and this range you can write like this. Okay, I'm not sure this. Okay, I couldn't check it actually. I'm sorry. Okay, when I teach to that the regular student also, I thought to find out whether this is correct or not, but I couldn't ask someone. Okay, so maybe you can ask your maths teacher or something whether this is correct. If you apply magnitude, that is okay to minus side and plus side, I hope. Okay. So that is, so I think that this will be correct, okay? But anyway, if this is not sure, you can write like this, okay? Omega c, omega is between plus omega c and minus omega c. Omega is between this one, plus minus 5 and minus omega c, like this, okay? So if can you draw this within this range? What is the magnitude of h omega in this range? Please tell me. What is the magnitude of h omega in this range? In this range, in this range, what is the magnitude of omega? What is the magnitude of omega? Magnitude of omega. What is the magnitude of omega? Ma- Sorry, magnitude of h omega. What is the magnitude of h omega? Magnitude of h omega. In this range, what is the magnitude of this h omega? Please tell me, that is very easy. What is the magnitude? Please tell me, what is the magnitude? In this range, okay, this range, okay, the omega is between minus omega c and plus omega c. Omega කියන එක මෙන්න මේ අතර මෙන්න මේ h omega වල magnitude එක කීයද? What is the magnitude of h omega? So that is very easy. Can anyone tell me what is the magnitude? Just give me answer as you know. What is the magnitude? Anyone there? What is the magnitude of this? What is this actually? What is this? What is this number? What is this number? What type of this number? What type of this expression? Okay, maybe you can remember that. Okay, if we have a complex number, okay, if we have a complex number, okay, this is the real axis, this is imaginary axis. Okay, so any complex number is said can be represented, okay, using this real part x and imaginary part. Yeah, okay. So instead you can represent as x plus iy. Okay, so this is the representation of the complex number. Okay, and what is this? What is this? This is we normally refer as r. That is the magnitude of z. That is equal to r. So what is the magnitude? Using the Pythagoras theorem, this r is equal to s square y square root. Okay, so this is the magnitude of the complex number. This is we referred as magnitude of the complex number. Okay, complex number. And if this is theta, that is the phase. That is the phase. Normally we refer this using this kind of angle mark. Phase of z, that is theta, it is equal to tan inverse using trigonometry. සම්මුඛ පාද බෙදීම බද්ධ පාද. Okay. So y divided by x. Okay. So this is the magnitude and phase of this complex number. Okay. And also, you know that z you can write as r cos theta and r sin x you can write as r cos theta, y you can write as r sin theta. This is r sin theta. This is r cos theta x. Okay. So you can write it. Okay. You can write it r cos theta plus I, because I is there, I r sin theta, like this. Okay. Then if you get this r out, it is cos theta plus I sin theta. What is cos theta plus sin theta? What is this? Can you remember the Euler formula? You know Euler formula. Euler formula is e to the power j theta. This can be plus or minus, is equal to cos theta plus or minus j sin theta. This is Euler formula. Okay. So this is using Euler formula. You can write this as, here it is plus. Okay. Z is equal to r e j theta. Okay. So this is also a complex number. This is also one representation of this Z. Okay. This is actually we call polar representation, polar form. This is we represent as rectangular form, rectangular form. Or it is called Cartesian form. Okay, this one. Okay, and also this can be written as, maybe you can remember that. Okay, r theta. That means this is also one representation of a complex number, the magnitude and the phase. So using the magnitude and phase, you can define, you can completely identify a complex number. Okay, you can completely solve this Z. Okay, what is x and what is y? If you know r and theta, r cos theta, r sin theta, then you can find this Z. Okay, so in this form also, this is the polar form, no? I can't remember. This may be the polar form. I can't remember. Okay, so anything. Okay. Then what is this? This one. What is this? Now I think you know. What is this? This is a complex number. Okay. Then what is the magnitude of this complex number? Then tell me what is the magnitude of this? Tell me the magnitude, please. What is the magnitude? This is a complex number, no? It is like this. It is like this. R E J theta. It is like this. So what is the magnitude of this complex number? Actually, this is a complex variable, okay? Complex variable. That is a number, but that number is varying because this omega is varying. This alpha is a constant, okay? So here also this theta and R is varying, no? Okay? If you consider general complex number, theta and R may be changing, okay? So different R and different theta will have different complex numbers, okay? So what is the magnitude of this? දැන් කියන්න මෙයාගේ magnitude එක. Now tell me the magnitude of this. මේක complex number එකක් නම් මෙයාගේ magnitude එක මොකක්ද? මේත් එක්ක බලන්න. Just compare with this one. This is a complex number R E J theta. මෙයාගේ magnitude එක මොකක්ද? What is the magnitude of this? R is the magnitude. Then what is the magnitude of this one? What is the magnitude? Did you understand this? This is a complex representation, okay? Complex number representation. This is actually complex number. If you consider, if you get the Euler formula, you will have C cos omega alpha plus I C sine omega alpha. So that is a complex number. Then what is the magnitude of this? R cos theta I sine I R sine theta. So you will have here, if you expand this, C cos omega alpha plus I C sine omega alpha. So what is the magnitude? That is C, okay? This magnitude is C, this one. This is the magnitude, okay? So here the R is the magnitude. Okay, so you can see this graph, okay? So this R is there. So that this R is the magnitude. This the length from here to here, that is we referred as magnitude of the complex number, okay? So that is the magnitude, okay? So the magnitude is like this. This is the magnitude. And between omega c and phi, what is the magnitude? 0. Because if you get the magnitude here, you will have 0. And between minus 5 and minus omega c, that is also 0. Okay? 0. Like this. Okay? Actually, this is not from to 0. Okay? After omega c, we can't say that up to infinity, this will be 0 because you know that, okay? So if you dissolve this, it is sine alpha cos alpha. No? Again, you can dissolve this into this one like this, r cos theta or sine theta. Okay, so you know that cos theta is equal to cos theta plus 2 phi. Sine theta also equal to cos theta plus 2 phi. Okay, so after 2 phi, this is repeating. So that means after here, if we get another phi here, so it is 2 phi. Okay. Okay, so this is repeating again like this. Like this. 2 5 to 2 5 omega c. Okay, then again this will be 3 5 like this. Okay, again at 4 5 this is repeating. Okay, so this will be repeating after that. Okay, so that is why I told you that. Okay, this is I am not sure. Okay, this is I am not sure. It should be between like this, minus 5 and minus omega c and plus 5 and plus omega c. Okay. Okay. Now just refer this one. Just refer this one. So you can see that within this range, within this range, within this range, okay, within this range, the gain is 1. Gain means y omega x omega. That is the gain. Okay. Actually, we get the what is called the magnitude. This is the gain. Okay. So now only the gain is there. Y omega is equal to C x omega. Y omega is equal to C x omega. Now the gain is C. Okay. So you have, if you are given input, you have output. Y omega is there. Okay. So that output is between this minus omega c and plus omega c within this range. Okay. So if you consider plus side, that is 0 to some frequency range. 0 to some frequency range. Okay. Then after that, the gain is 0. That means y omega is 0. There is no output for the filter. Okay. With after this range, no output. Output is 0. So that means from here to here, the filter is filtered. Okay, it is not passing this frequency, it is just stop the frequency, this frequency. Okay, so these are low frequency and these are high frequency. Okay, so this filter pass only low frequency. This filter can pass only low frequencies. That means this is a low pass filter. Okay, this is a low pass filter. Okay, so this is a low pass filter, ideal low pass filter. Okay, and the response is like this. Response is like this, and you can represent it like this within this limit. Okay, and also if it is a high pass filter, that means, okay, if it is a high pass filter, that means, okay, that means the filter gain should be there for a high frequency. High frequency. Omega c to 5, the filter gain should be there. Okay. And omega c to minus 5, filter gain should be there. But this frequency, the filter gain should be 0. Okay. So high pass filter, you can represent like this. Okay. H omega is equal to 0. Omega c minus omega c and plus omega c, and c e to the power j omega alpha minus omega c to minus 5, okay, sorry, minus 5 to minus omega c and plus omega c to 5, okay. So maybe you can represent using the magnitude here. In this range only, the gain is there, gain is there, gain is there. If you put the magnitude of h omega with respect to omega, the gain is there, okay? And here, no gain. So that is the high pass filter, okay? Ideal high pass filter. But actual response will not like this, okay? So, 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 so this is the ideal response, and I have shown you the actual response, okay? Actual response, the practical response. The practical realizable response may be like this, okay? So you can see that this is a low pass filter, okay? So 0 to some cutoff range, okay? So here you have like this, okay? It is going like this, okay? But now for the realizable, actual realizable filter, so it is not very sharp, okay? So it has a slope like this, okay? Okay, so that is the practical filter. Okay, for a practical filter, this has a slope like this, maybe like this. Okay, and sometimes this has a ripple also, and here also sometimes has a ripple. Okay, so this is the practical. The red one is the practical realizable one. This green one is the ideal one. Okay, so here also the same. Okay, so if you consider a band pass filter, I think now you can write it. Okay, band pass filter, band pass filter. Okay, band pass filter. Okay, that means that will pass h omega magnitude. Okay. So omega is between some specific range, within this range, specific range. Okay. And this also, the minus side also will be there. Minus omega 2 and minus omega 1, this range. Okay. This range. Okay. And here it is to 5. Here it is up to minus 5, this omega. Okay. So only this range, you will have the gain. Okay. So you can write this as h omega is c e to the power minus j omega alpha when omega is omega 1 and omega 2 and also minus omega 2 and omega 1. So I think you can put magnitude here. Okay. And 0 within this range. 0 to omega 1, it is 0. 0 to omega 1, it is 0. So this is 0 to omega 1, 0. Then omega 2 to 5, also 0. Omega 2, omega 5. This is also 0. In this range and this range, it is 0. So this is the band pass filter. Okay. Then band stop filter means, okay, this is ideal. Okay. So that means it stop specific frequency like this. Okay. So this omega 1, omega 2, it is stop and other pass until up to plus 5. If this is omega 1, omega 2, this is passing minus 5. So gain is there between minus 5 minus omega 2 and uh, and omega 2 to 5 and omega 1 to between minus omega 1 and plus omega 1. The gain is there. In this range, gain is there. Between omega 1 and omega 2, gain is 0. That means this band is not passing through this filter. Okay. So that is the band stop filter. Okay. So these 4 classifications are there. Okay. You need to be you need to be familiar with this. I hope you have learned this before also. This is the most basic fundamental classification of a filter. Frequency selective filter. Okay. Low pass, high pass, band pass, and band stop. Okay. So that is that. Okay. Then, uh, then, so I told you that based on uh, the impulse response, Hn, based on the impulse response, also we can classify a filter into 2 types basically. Okay. That is based on Hn. Okay. Based on impulse. Based on the impulse response. Based on the impulse response. Okay. Hn. We can classify a filter into 2 types, that is FIR and IIR. FIR means finite impulse response, okay. Finite impulse response. IIR means infinite impulse response, okay. Infinite impulse response. Finite impulse response and infinite impulse response. Then what is finite impulse response? Finite impulse response means impulse response has finite sample, countable sample. If Hn, the impulse response has finite sample, it is referred as finite impulse response. Okay. And if the impulse response has infinite sample, it is referred as, okay, infinite impulse response. Okay. So it has the Hn has a infinite number of sample. Okay. So that is FIR and II. Okay. for example, let's say that, okay, let's say that you are given an impulse response. That impulse response is somewhat like this: 2, 0, 1, 2, -1. Let's say that this is the zeroth sample. Okay. So tell me, okay, so this is the impulse response of a filter. You are given one example, okay? So as example, you are given the impulse response of a filter, okay? So tell me that, is this FIR or IIR? Tell me whether this is FIR or IIR. Quickly tell me. I think all of you should be able to answer, okay? Is this FIR or IIR? Okay, I didn't get any answer. I think that is very simple. Okay, so you can see that here we have 1, 2, 3, 4, 5 samples. 1, 2, 3, 4, 5 samples. If I plot this HN, if I plot this HN, okay, so zeroth sample is 1. Okay, zeroth sample is 1. -1 sample is 0. Minus second sample is 2. First sample is 2. 1, 2. Second sample is -1. Okay. So this is the impulse response, Hn, with respect to n. Okay. So you can see that 1, 2, 3, 4, 5 samples are there. 1, 2, 3, 4, 5 samples are there. Okay. So 5 samples are there. That means finite sample, no, only 5 samples. Yeah. So this will be a 5R field. Finite impulse response. This Hn is a finite impulse response. Okay. I think it is better if you can in line with me, okay? Because if you have any problem, you can ask me, okay? So anyway, if I give you another HN impulse response, let's say this is the first impulse response. I will if I give you another impulse response, let's say that's half NUN, this kind of one. Is this FIR or IIR? Is this FIR or IIR? Okay. This UN means, okay, UN, you know that unit impulse, unit step signal, okay? So discrete time unit step signal is like this, up to infinity, 0, 1, 2, so 1, 1, 1, up to infinity, okay? So this is unit step signal. So UN is there to give a range to n. So this n will be from 0 to infinity, okay? Half n, okay? So your response will be here, the zeroth will be half, okay? Then it will be 1 by 4, then it will be 1 by 8, 1 by 16, so on up to infinity, okay? So there are infinite sum. So here, infinite sum. So this is definitely a infinite impulse response, okay? So that is FIR and IIR, okay? So that is first thing you should understand, okay? First thing you should understand, okay? So if we are given H omega, or if we have found H omega, okay? If we are given or found H omega, that is the response, okay? If we are given the response, if we are given the response, okay? Given the response, we can conclude the impulse response Hm from H omega, okay? Okay. This Hn should be finite impulse response, okay? So we can conclude this finite impulse response Hn, okay? Uh, Basically, we are using two techniques, okay? Using two techniques. One is we called windowing techniques. Windowing technique, okay? Then other one is frequency sampling technique. Frequency sampling technique, okay? So these are the most popular techniques to conclude the FIR-HN, finite impulse response of the filter, if we are given the response H omega, okay? Uh, so these are called filter techniques, okay? Filter design techniques, okay? So basically we have two FIR filter design technique, okay? Filter design technique. That is, as I told you, windowing technique and frequency sampling technique, Okay. So both are very straightforward and very simple, okay? These two techniques, okay? So I will explain this windowing techniques because in Dr. Udesh lectures, I couldn't see the frequency sampling technique, so it will not come to the exam, okay? So because we are now very near to the exam, we will only focus in on this one, windowing technique, okay? So that is one uh, simple techniques to design a FIR filter. Actually, designing means we are concluding the HN, okay? So that is our design. We refer to design to conclude the HN, okay? So this windowing technique is one very popular techniques to conclude the HN if H omega is given, okay? Okay, okay. Let's say that you are given a response H omega, okay? So you are given response H omega, then you have to find the Hn. So that is, to find the Hn actually, what you have to do, you have to apply the inverse Fourier transform. You have to apply, okay? Then, uh, then this Hn will be a IIR Hn, infinite impulse response, okay? Because n is not defined, n is not limited, okay? So we have to limit the n using this windowing techniques, okay? So we are finding the finite impulse response. Normally we referred it as desired impulse response. Okay, this D denote the desired. Okay, so we are finding the desired impulse response. Okay, using the window techniques. That means simply we are multiplying the obtained infinite impulse response, multiplying. Okay, just multiply. Not, this is not a convolution. Okay, this just multiply by a window function W. Okay. So I will explain what is this window function. Before that, there are many type of this window function. Okay, many type of this window function. I think 4 or 5 window functions are there. Okay, so in like Dr. Udesh lecture also, you can um, find it. Okay. Mm. So these are some windowing techniques. Okay. Um, actually one is called rectangular window. Okay. So that is the most fundamental window, rectangular window. It is not mentioned here. Okay. Rectangular window. And Blackman window, Hamin window, Hanin window, Bartlett, okay. And there are some case likewise, okay. So there are some window functions, okay. There are some basic Windows functions there, okay. Uh, as I told you, okay. So the most fundamental windowing function is the rectangular window, rectangular window, rectangular, okay. So what is okay, rectangular window, okay. So that is very simple, okay. So let's say that it is somewhat like this, okay. So let's say that you are asked to get, you are asked to get uh, m number of samples, for the HN, okay, for the desired HN, you need to get m number of samples, okay. Then you can define your Wn as, okay, Wn as 1, 1, 1, 1. So this is the 0th sample, 0 to number of m. Okay, so this 1 should be come to m minus 1, up to m minus 0 to m minus 1 sample. So there are total m number of samples. Okay, you can define your window function like this. Okay, so let's say that we will get the example 2 again. Example 2 again. Okay. So let's say that you are given Hn. Okay. You are given Hn, that is half n U, this kind of. Okay. Then you are asked to get only 4 sample, 4 sample, only 4 sample using windowing technique. Using windowing technique, sorry, rectangular windowing technique. Rectangular windowing techniques. Okay, so you are asked to get 4 sample using rectangular windowing technique. Okay, so this so now you can see that if you consider this Hn, that is infinite impulse response, because n is going from 0 to plus infinity. So n is from 0 to infinity, 0, 1, 2, 3, 4, 5, so on up to infinity, this Hn, okay. And if you if you write this, okay, so this is the first one, the n is equal to 0, that is n is equal to 0, that is 1, half 0, that is 1, okay. N is equal to 1, that is 1 by 1, 1, so it will be half, okay, it will be half. Then square, n is equal to v square, that means 1 by 4, 1 by 4. Then it is 3 to the power, that is 1 by 8. Then 1 by 16, 1 by 32. So on, it is goes up to infinity. So this is your HN, okay. So there are infinite number of infinite number of samples in this section. Okay. Okay. Sample infinite nothing. Okay. Now you are asked to get only 4 samples, 0 to 1. Okay. That means you have to define your window function Wn, that is 1, 1, 1 up to 4. There should be 4 samples only. So 1, 1, 1, only 4 samples. So this will be the 0th one, and this will be the 4 minus 1. That means m minus 1. Okay. So that is how I define this. Okay. 1, 1, 1 up to m minus 1, because the 0th sample is including here. So m, so you have to get up to m minus 1 sample m minus 1. Okay. So you will have, this is the third sample, 0th sample, first sample, second, third. Okay. So the window function you will get like this. This is n, this is Wn. If this is a rectangular, you will get this one, 1, this one, 1, 1, 1. So this will be 0, 1, 2, 3. Okay. Now what you have to do? To find the desired response, HDN, you have to multiply the obtained HN with the defined rectangular window. Okay. So normally rectangular, to express rectangular window, we use R here, omega Rn. Okay. So what you have to do, you can just multiply. Okay. Then you can see that, so here there is no sample, here also there is no sample. So 1 into 1, you will have 1. Okay. Then half into 1, you will have half. Then 1 by 4 into 1, you will have 1 by 4. Then 1 by 8 into 1, you will have 1 by 8. Okay. Then 1 by 16 into 0, 1 by 13 into 0. So all these things will be 0. From here to here, you will have only 0. So you, in your desired response, you will have only these countable sample number. So that is your desired impulse response. So you will have only 4 sample. So this will be a FIR, finite impulse response filter. Correct? Okay. So that is thing. Okay. Okay. Now I will get one example. Okay. So I will give you one example. Okay. So let's say that low pass filter response is given as, maybe you can remember, H omega is equal to C e to the power minus J alpha omega and 0. So this will be omega is between minus omega C and plus omega C. Okay. This should not be there. Okay. Minus omega C and plus omega C. And 0 if the omega is between minus 5 and minus omega C, and omega is between omega C and plus 5. Okay. So this is what we have discussed. Okay. This is the low pass filter is given as like this. Okay. Now I you asked to find or design a FIR filter, finite impulse response filter with M sample, using rectangular window. So then can you try to evaluate this? Okay. So what you have to do is, first H omega is given. So first thing you have to apply inverse Fourier transform. Then you have to find Hn. That is the first thing you should do. You have to find Hn. Okay. Then the n is not limited here. Now you are going to have m number of sample. That means you have to use the windowing techniques to get the desired impulse response, that means you have to multiply your obtained Hn by the rectangular window function. Okay, so that is what you have to do. Very simple. Okay, very simple. Okay, so maybe you can't remember the inverse Fourier transform identity. Okay, so you know that if we have H omega, if we apply Fourier transform, we will have, sorry, if we have a time domain signal Hn, okay, if we apply Fourier transform, we will have H omega, the Fourier transform, the frequency domain signal. This is the time domain signal. Then this is the frequency domain signal. Now, if you have apply inverse Fourier transform, okay, to this H omega, again, by using this frequency domain signal, you can get Hn, okay. So that is we call Fourier transform pair, okay. So you have to use inverse Fourier transform of H omega, okay. So then you will get the time domain signal back, okay. So it is like this 1/2 minus infinity to plus infinity H omega e to the power j omega j omega n d omega. This is the inverse Fourier transform definition, okay. Minus infinity apply this one, okay. So try to find the, so you can use this one, okay. First try to find the inverse Fourier transform of this section. So what you have to do, we will verify this correct or not, okay. This is your, okay. And frequency domain analysis, okay. Frequency domain analysis of LTI system, frequency analysis of signal, okay. Under frequency analysis of signal, we have designed, we have learned the Fourier transform, okay. Maybe you can remember, okay. This is for continuous time. This is Fourier series for continuous time. We are not, we don't need to follow that one because we are mainly discrete, we are mainly dealing with discrete time signal, okay. So this is the continuous time again, no need, okay. And this is discrete time version. So this is the Fourier series representation. You should familiar with this one, okay. And this is Fourier transform, okay. Discrete time Fourier transform, you have to familiar with this one, okay. So this is the Fourier transform, okay. Fourier transform for a discrete time signal, you have to do the summation, but we learned that this omega will not be a discrete value. It will be a continuous value because omega is not defined as discrete, okay. So omega will be a uh, continuous variable, okay. So omega is a continuous variable. When you are finding the inverse Fourier transform, you have to apply the what is called integration, okay. So that is plus j omega n. That is what I want to verify. It will be plus j omega n 1/2 within 2 ohm. So you can apply, this is one in minus infinity to plus infinity, but this omega is a discrete time one, discrete. So normalized one, actually not discrete, this is a normalized omega. So normalized omega is between -5 and +5. That is why it mentioned as 2π. Okay. So this is the identity for a discrete time inverse Fourier transform. Okay. So it is same as continuous time Fourier transform because this omega uh, is a continuous variable, but as I can remember, in a continuous time, this can be minus infinity to plus infinity because this omega is not normalized. So it can be minus infinity to plus infinity. Okay. But in normalized case, it should be minus 5 to plus 5. That is why it is mentioned as 2, 5. Okay. So this one you have to remember or familiar. Okay. Better to remember. Try to remember this. Okay. These are some basic equation. Okay. And maybe you can remember that if you want to get the sampled frequency, okay, so that means if we sample this frequency, okay, we will have a discrete frequency that is we called as discrete Fourier transform. Okay, actually, so that is also you should be familiar. Okay, actually, as I told you that there are two types of filter design. One is frequency sampling method. Okay. So frequency sampling techniques. In these techniques, we use discrete Fourier transform rather than using inverse Fourier transform. Discrete Fourier transform we have to apply. Okay. But that part will not be covered. Okay. So only this one, that is enough to familiar with the windowing technique. Okay. So anyway, try to evaluate this integration and find the inverse Fourier transform of H omega. This one. Okay. So try to evaluate the inverse Fourier transform of this one. Okay. Using this identity. Okay. So try to do it. I will give you 5 minutes. Try to do it by yourself. Okay. Okay, I will do it. Okay. So, we are given H omega. Okay. We are given H omega. Okay. So H omega is given as e to the power C e to the power J alpha omega. This is minus. Okay. So this omega C, omega is between minus omega C and plus omega C. Okay. And 0, the omega is between minus 5 and minus omega C and plus omega C plus 5. Okay. So this is the given H omega. Okay. So first, what you have to do, first you have to find the impulse response Hn by applying the inverse Fourier transform to this H omega. Okay. So that is 1 over 5. Okay. So I will write here, this is minus 5 to plus 5 because this one, so this H omega is actually defined between minus 5 and plus 5. Okay. Because the omega is the normalizing one. So it is minus 5 and plus 5. So if it is going, this same thing is repeating. Okay. So up to minus 5 and plus 5, that is enough. Okay. It is somewhat like this. Okay. Up to minus omega C, this is plus omega C. This will be clearly. Okay. So your H omega, something like this. Okay. Omega, H omega. So if I go the magnitude, okay, minus omega C plus omega C plus omega C plus 5 minus 5. Okay. So you will have the gain is 1. And in this case, gain are 6. Okay. So your omega is between minus 5 and plus 5. So I will put that. Okay. I will put like this. Okay. And H omega e to the power j omega n e omega. This is the inverse Fourier transform. Okay. So now you can apply 1 over 2, 5. Okay. So you can see that minus 5 to minus omega c, it will be 0. Okay. So that part will be cancelled. Minus omega c to plus omega c. Minus omega c to plus omega c. This H omega will be this C e to the power minus j alpha omega, e to the power j omega n, d omega, okay, plus omega c to minus omega c to 5, again it will be 0, so that also will be 0, okay. So you have to evaluate only this one. Okay, you have to evaluate only this one. So this is very easy, this evaluation, okay. So you can write omega c and plus omega c, okay. So c is a constant, you can get it out, okay. So e to the power, if you get this j omega out, you will have n minus alpha d omega, okay. So this is now you can easily integrate, okay. You know that this omega is only, so you have to consider this omega as the variable. So n is a constant in this case, okay? But n is actually variable, but you have to consider because you have to do the integration with respect to omega only, okay? So this n can be considered as a constant, okay? Then you can evaluate this like this, j omega n green alpha divided by j n green alpha, n minus alpha, okay? So this is the evaluation, okay? And you have to apply the limits from minus omega c to plus omega c, okay? So now you have to apply these limits, okay? So actually you are finding hn, okay? So hn will be c to 5, okay? So if you apply the limit for this omega, okay? So here you can, this also a constant, okay? So you can write here j n minus alpha, okay? So if you consider this one, you will have e to the power, so you have to apply the upper limit, e to the power j omega c n minus alpha minus e to the, now upper limit minus omega c. So you will have minus j omega c n minus alpha, okay? So what is this? Okay, so you know that using Euler formula, okay? E j theta is equal to cos theta plus j sin theta. E minus j theta is equal to cos theta minus j sin theta. So if you subtract 2 from 1, okay, e j theta minus e minus j theta, cos theta cancel out, j sin theta minus j sin theta, so you will have 2 j sin theta, okay. So e j theta minus e j theta minus e minus j theta is equal to 2 j sin theta. So this is equal to 2 j sin theta or something, okay. So you will have hn as c to 5j n minus alpha, okay. So this is this is theta, okay. This term is identical to theta. So e j theta minus e minus j theta, you will have 2j sine theta is identical to this one, omega c n minus alpha, omega c n minus alpha, please say, okay. So j and j cancel, so hn you have c divided by 2 5, okay, 2 5. So this 2 also cancel, c divided by 5 n minus alpha sine omega c n minus alpha. So this is the hn, okay, this is the impulse response, okay. So the obtained impulse response hn is equal to c 5 n minus alpha sine omega c n minus alpha. So this is the obtained impulse response hn. Okay. So now you are asked to find the desired impulse response, okay? Desired impulse response by using rectangular window, okay? WR rectangular window, okay? With M sample, with M sample. So you can define the rectangular window as 1, 1, 1 up to M minus 1. The 1 is there. So this will be 0. So there are total m sample. So you have to, so here you can see that n is not limit, okay? Here n is not limit. N can get any value, minus infinity, plus infinity. So definitely this will be IIR, infinite impulse response, okay? So now you have to find the FIR response, finite impulse response, that is your desired response using windowing techniques, okay? So you have to multiply this window, okay? So once you multiply, you can write this HN as, okay, this one, this term, okay, this term, I will not write this term. That term is available when n is from 0 to m minus 1, okay, and 0 otherwise. So that is your desired response, HD, desired response. So this will be the FIR. Okay. So that is that. Okay. Okay. Now, if you consider, so now I will give you two homework to do. Okay. So if you consider rectangular window, it is somewhat like this. One, if n is between 0 and m minus 1, okay, and 0 otherwise, 0 otherwise. So this n is time domain, no? N is time domain, okay? So find the frequency domain of this WR omega, okay? So that is you have to use the Fourier transform, okay? Fourier transform, discrete Fourier transform. That is you can get WR omega by getting n from minus infinity to plus infinity. In this case, it is 0 to m minus 1, okay? 0 to m minus 1, Wn is equal 1 at this time. 1, okay? 1 e to the power minus j omega n, okay? So n from 0 to m minus 1, try to find this omega r, okay? This omega r actually, if I find it, it is very easy, okay? It is not much difficult, okay? So so I'm finding the Fourier transform of this window, okay? Fourier transform of window, okay? That means the frequency domain window, because this window is given in time domain, n is the time domain, okay? Now I want to connect it to frequency domain, okay? So it will be n is 0, that means 1 plus, then n is 1, e to the power minus j omega, then n is 2, e to the power minus 2 j omega, n is 3, e to the power minus 3 j omega, so on up to m minus 1, e to the power minus m minus 1 j omega. Okay, so you will have this one, okay? So you can get the compact solution to this one using this identity. I think we have done it in, this is one expansion, Taylor series expansion, okay, up to infinity. You can write it as 1 over 1 minus a in this form, okay. So this is Maclaurin expansion, one of Taylor series expansion, Maclaurin expansion. Using this one, you can get the compact value for this omega r, okay. Compact value for this omega, okay. So if I evaluate that one also, okay. So so this is that, okay, 1 plus a square plus a third up to infinity. So you will have 1 minus 1 into 1 divided by 1 minus a, okay. And you have to find m minus 1, okay. So m minus 1. So you can you can multiply this by am, okay. You can multiply this by am, okay. So if you let's say that this is 1, so you multiplied 1 using am. So you will have here AM plus A, M plus 1 plus A, M plus 2, so on up to infinity. Okay, so that will be AM 1 minus A, because you have multiplied by this AM. Okay, the same thing we have done. Okay, now let's say that this is second. Okay, so you have to get 1 minus 2. Okay, so you can see that. So here also 1 A square A3, so on, it comes to AM minus 1 plus AM. Okay, so now if you subtract 1, 2 from 1, so you can see that this AM cancel, AM plus, AM 1 plus cancel, AM uh, plus 2, those are cancelled up to infinity. Okay, and you will have up to 1 plus A square, 1 plus A square, A third, so on up to A n minus 1, capital N minus 1. Okay, so that is you will have, so you that answer you will have A 1 minus A minus AM 1 minus A. So you will have 1 minus AM divided by 1A. Okay, so this is the compact solution we will have. Okay, so so you can write this term as e to the power minus j omega 1 plus e to the power minus j omega 2, so on. Okay, so in this case, A is equal to, okay, in our case, okay, A is equal to e to the power j omega. So you have to apply the e to the power j omega here. So your WR omega, the frequency domain window, rectangular window will come y1 minus e to the power j omega m divided by 1 minus e to the power minus j omega. Okay, so you will have this one. Okay, so maybe you can remember that if you get out e to the power minus j omega m divided by 2, you can write this in terms of sign, or sign terms also. So maybe you can try to write in sign terms also. Okay, anyway, this is the response. Okay, this is the response of the window. Okay, now if you plot the magnitude of this omega r, if you plot the magnitude of this omega r, okay, so you have to plot the absolute value, this one, absolute value of this. Okay, if we plot the absolute value of this, okay, absolute value of this term, okay, with respect to omega, okay, so you will have a function somewhat like this. Okay, so maybe you can check, maybe you can plot this in MATLAB. Okay, so you have to plot the uh, with h omega, absolute of omega, WMO, absolute value, ABS value of uh, omega, sorry, WR omega, okay, with respect to omega. Okay, so you will have this kind of function. Okay, okay. Uh, so this is also we use to evaluate something, actually mainly to find the side lobes of the filter. Okay, so we will learn them later if needed. Okay, maybe next week or something, or maybe in, if you have time, we can put one class in Thursday also. Okay, so this one also somewhat important. This is also evaluating Dr. Udesh lecture note. That is why I write it. Okay, so here we have find the frequency response of the rectangle, the sorry, rectangular window function. Okay, frequency response of the window function. So it is somewhat like this. Okay, it is somewhat like this. This one we use to mainly to estimate the slide lobes of the filter. I will explain it. Okay, what is that? Okay, so anyway, I will give you one example to do. Okay, one example. Okay, let's say that you are asked to design. Okay, so let's say that you are asked to design design a finite impulse response filter, okay, filter, low pass, okay, low pass finite impulse response filter, okay, with, um, let's say that 5 sample, with 5 sample, okay, using rectangular, rectangular window technique, window technique, okay, technique, okay. Let's say that your your cutoff frequency FC is 100 hertz, okay, and your sample frequency Fs is um, 10,000 hertz, okay, 10,000 hertz, okay. Then you are given the response as, you are given the response as H omega. So you will have some numerical value here, e to the power j 5 omega minus j 5 omega and 0. So you know that omega is between omega c and plus omega c, and omega is between omega c and minus omega c and plus omega c, and omega is between omega c and 5. Okay, I will put omega here, magnitude here. That means minus omega c to minus 5 and omega c to plus 5. Okay. Okay, so this is the response you are given. Okay, and you are asked to design like this. Okay, now you say, you can see that you are given some frequencies in hertz. Okay, so first you have to use this one. Okay, first you have to find the normalized frequency, normalized frequency, normalized frequency of the filter. Okay, normalized frequency of the filter. So that is frequency divided by the sampling frequency, that is the normalized frequency. Okay, then you have to find the normalized omega using 25f. Okay, so omega is equal to 25f. Using this one, you can calculate the normalized cutoff frequency. Actually, that is this one and this one. Okay, then what you have to, you have all the information. Then you have to do the integration between minus omega c and plus omega c. You have to find it in this way. Okay. Then you have to apply the rectangular window function to have 5 samples. Okay. So finally, in your desired response, okay, you will have only 5 samples. Okay, only 5 samples. Okay, 5 samples. Okay. Then if I ask you to design the same filter using another windowing technique, let's say that you have to use another windowing technique. That is the window techniques. Let's say that you have to use this one, Hanning techniques, okay? Using Hanning window, okay? If I ask you to define using Hanning window, uh, what is the desired response, okay? So you have to find the desired response using rectangular and desired response using Hanning, okay? Okay, you have to find the desired impulse response using rectangular, and you have to find the desired response using Hanning also. Okay, so try to find these two. Okay, okay. So Hanning techniques, you have to calculate the value. Okay, so in rectangular window, you don't need any calculation. You have to get 1, 2, 3, 4, 5, 6, any sample. Okay, but if you find Hanning, then okay, so you have to calculate. Okay, you have to calculate this value. Okay, like this. Okay, okay. For example, if the n is 0, you have to calculate the zero value by applied 0 here. So cos 0 is 1, no? So zero point 0.5 minus zero point 0.5, you will have 0 here. Okay, you will have 0. Cos 0 is 0. I don't know. Okay, okay. So it will be 0. Okay, how will it comes here? Okay, use Hamin. Okay, Hamin, just use Hamin. Okay, okay. So here in cos 0 is there, so you can calculate the first sample, then apply N2, you can calculate the second sample. So you have to calculate the five samples, then you have to multiply. Okay, you have to find the HD, the desired response, then you have to find the HN using this information, then you have to multiply and find the desired response. Okay, so try to do this question, try to do this example at home. Design a low-pass FIR filter with 5 samples using rectangular window and also Hamming window techniques. Okay, so cutoff frequency is 100 hertz and sampling frequency is uh, uh, 10,000 hertz. Okay, so your response is given as e to the power minus j 5m. Okay, so that is what you have to do. Okay, so try to do that one at home. Okay, so wait a moment. I will so write this one. Okay, first write this one. Then wait a minute. I will I will give you, I will, so you need to mark the attendance, okay? So wait a moment. Okay, mark the attendance, okay? So if you have any problem, you can ask me, okay? If you can have any problem, you can ask me. Otherwise, you can leave after marking the attendance, okay? So if any problem, you can ask me.